We have already studied the graph of a sine function and a cosine function. Now, following a similar approach, we can evaluate the other 4 trigonometric function values for various angles and plot the solution points and make the graphs for tangent function, cotangent function, secant function, and cosecant function. Just like in the sine function and cosine function, the independent variable x is an angle given in the unit of radian. This is a graph for the tangent function fx equals to tangent x. From the graph, you can see that the shape is a reversed S shape and it is repeated, and therefore we can tell from the graph that tangent function is a periodic function with a period of 1 pi. If you recall, when we were studying how to evaluate the tangent function, tangent x equals to sine x over cosine x. Therefore, whenever cosine x equals to 0, tangent x is undefined. And cosine x equals to 0 when x equals to either half a pi or negative half a pi or 3/2 pi, etc. And on the graph, you can see that that corresponds to the vertical asymptotes of the tangent function. So the vertical asymptotes are when x equals to n pi plus half a pi. N can be any integer, positive, negative, or 0. And since tangent x is undefined for these x values, therefore these x values are excluded from the domain. Therefore, for the tangent function, the domain is x can be any other real number except for n pi plus half a pi. And from the graph, you can see that the range for the tangent function includes all real number from negative infinity to positive infinity. And the graph is indeed symmetric about the origin. Therefore, tangent function is an odd function. And lastly, within each period, tangent function is always increasing. Here is the graph for the cotangent function fx equals to cotangent x. As you can see, the shape of the graph looks like the mirror image of the tangent function. Cotangent function is also periodic with a period again of 1 pi. Because cotangent x equals to cosine x over sine x, therefore cotangent x is undefined whenever sine x is 0, and that corresponds to when x equals to either 0 or pi or 2 pi, etc. And on the graph, once again, you can see that those x values correspond to the vertical asymptotes for the cotangent function, which is x equals to n pi. Once again, n can be any integer. Therefore, these x values are excluded from the domain for the cotangent function. Therefore, the domain here is x can be any real number except for n pi. Once again, the range for the cotangent function also includes all real number from negative infinity to positive infinity. And the graph is also symmetric about the origin. Therefore, cotangent function is also an odd function. And lastly, within each period, the cotangent function is always decreasing. Here is the graph for the secant function fx equals to secant x. The shape of the graph looks like a series of up and down U-shapes, but since secant x is related to cosine x, secant x equals to 1 over cosine x. Therefore, one way to remember the shape of the secant function is to know that you can actually draw the graph of the cosine function snugly between the graph of the secant function. And since again, secant x equals to 1 over cosine x, whenever cosine x is 0, secant x is undefined. So once again, secant function also have these vertical asymptotes that x equals to n pi plus half a pi, again corresponding to the angles when cosine x equals to 0. And therefore, these x values are excluded from the domain for the secant function. And from the graph, you can see that secant function has the range from negative infinity to negative 1, including negative 1, and from positive 1 to positive infinity, including positive 1. Secant function is also a periodic function. It has the same period as a cosine function, which is 2 pi. And lastly, since cosine function is an even function, therefore secant function is also an even function. You can see from the graph that its graph is indeed symmetric about the y-axis. Lastly, this is the graph for the cosecant function, fx equals to cosecant x. As you can see, this graph looks just like the graph for the secant function with a horizontal shift to the right by half a pi. And since cosecant x equals to 1 over sine x, this graph is related to the graph of the sine function in the way that you can draw the sine function graph in between here. And once again, since cosecant x equals to 1 over sine x, whenever sine x equals to 0, cosecant x is undefined, and that corresponds to the vertical asymptotes for the cosecant function. X equals to n pi, these are the vertical asymptotes, and they need to be excluded from the domain for the cosecant function. And from the graph, you can see that the range for the cosecant function includes from negative infinity to negative 1, and then from 1 to positive infinity, the same range as the secant function. And since cosecant function equals to, once again, 1 over sine, therefore, since the sine function is an odd function, cosecant function is also odd function. And on the graph, you can see that the graph is indeed symmetric about the origin. And lastly, just like the sine function, cosecant function has the period of 2 pi. Let me remind you again of the transformation rules when we want to graph a new function based on its parent function. And then we will look at two simple examples. So here, function gx is related to the fx function through a, b, c, d, these 4 coefficients. Let's start from within the parentheses. This coefficient b here is responsible of horizontal stretching, shrinking, or reflection. Therefore, for a trigonometric function, it's going to change the period of the function. This coefficient c here is responsible of horizontal shifting. This coefficient a here is responsible of vertical stretching, shrinking, or reflection. And lastly, this coefficient d here is responsible of vertical shifting. So let's look at this example. We need to sketch this gx function. Gx equals to tangent 3x minus half a pi. And we recognize that the parent function is a tangent function. And this is what the parent function graph looks like. Now, since this graph is periodic, we only need to graph one period because before or after this period, the graph simply repeats itself. Therefore, we recognize that for the parent tangent function, this period starts at x equals to negative half a pi and it ends at x equals to half a pi. Therefore, we want to find the start point and the end point for the first period for our new gx function by equating this part right here, what's inside this parentheses, to be negative half a pi and positive half a pi. Therefore, for the new start point, 3x minus half a pi equals to the start point that we read from our parent function, negative half a pi. From this equation, we can solve for x to be 0. So that's the new start point. For the new end point, we equate 3x minus half a pi equals to positive half a pi, which is the end point that we read for this first period from our parent tangent function graph. And from this equation, we can solve for x to be positive third pi, which is the new endpoint. So based on that calculation, when we are going to sketch the first period of this new gx function, we start from 0 and we end at x equals to third pi. Third pi minus 0 equals to third pi, which means that this gx function has a period of third pi, and this agrees with the general rule that we learned before, since this coefficient indicates a horizontal shrinking by the factor of 3. Therefore, to calculate the new period for this function, it equals to pi over this coefficient 3. Here, it is pi because, don't forget, for the parent tangent and cotangent function, their period is 1 pi. Versus for the sine, cosine, secant, cosecant functions, the parent function has a period of 2 pi. So remember that difference. So based on all this information, we can mark our coordinate system, find our start point and end point, 0 and third pi, and within this interval, we draw the first period of tangent function. And then we repeat this graph for several more periods, and this completes the graph for our new gx function. Let's look at this example to sketch the function gx equals to negative cotangent half a pi x plus pi. So we recognize that the parent function is a cotangent function, and this is what the parent function looks like. If we are going to only focus on the first period, we notice that the first period of this cotangent function starts from x equals to 0 and ends at x equals to pi. Therefore, to find the new start point and end point for our new gx function, we equate this part to 0 and pi. So for the new start point, half a pi x plus pi equals to 0. To solve x from this equation, we get x equals to negative 2. And then for the new end point, half a pi times x plus pi equals to the end point for our parent function, which is 1 pi. Therefore, from this equation, we can solve x to be 0. Based on that calculation, to sketch the first period of our gx function, we start from x equals to negative 2 and end at x equals to 0. 0 minus negative 2 equals to positive 2, which indicates that for our new gx function, it has a period of 2. And again, that agrees with this period calculation, pi over absolute value of the b coefficient. In this case, the b coefficient is half a pi. Once again, period equals to pi over b instead of 2 pi over b is because for a cotangent function, the parent function has a period of 1 pi. Therefore, pi over half a pi equals to 2. So based on this information, we mark our coordinate system, find our start point and end point, negative 2 and 0. So within this period, we want to sketch the parent tangent function, which has this S shape. However, don't forget, we have a negative sign here, and this indicates a vertical reflection. Therefore, instead of sketching this cotangent parent function shape, we flip it about the x-axis, and then we sketch some more periods, and this completes this problem. This is the graph for the function gx equals to negative cotangent half a pi x plus pi.